Welcome to Lecture 6 of the Introduction to ICT course. In this session, we will explore number system arithmetic, a foundational topic in computer science and digital electronics. This topic includes the arithmetic operations of addition and subtraction as applied to 4 different number systems: decimal, binary, octal, and hexadecimal. More than just a math lesson, these operations are critical for programming, networking, hardware design, and cybersecurity. Segment 1. Arithmetic in the decimal system, base 10. Decimal arithmetic is used daily in banking, accounting, billing software, and data entry systems. Every price you see on an e-commerce website, every tax calculation, and every payroll system uses decimal math behind the scenes. The decimal system is the one we're most familiar with. It uses digits from 0 to 9 and is based on powers of 10. Let's learn how to perform addition and subtraction with decimals, particularly those involving fractional parts. We start by aligning the decimal points. This helps us keep digits of the same place value in line. Then we simply add column by column, starting from the right. 4 plus 6 gives us 10, so we write down 0 and carry over 1 to the next column. Continuing this process, we get the final result: 474.0. Again, align the decimal points. Subtract column by column starting from the right. We perform the subtraction as we would with whole numbers, making sure to keep the decimal point in the correct place. The answer is 210.50. Segment 2. Binary arithmetic, base 2. Binary numbers are at the core of computer operations, digital logic circuits, and IP addressing in networking. When you write a low-level program or calculate subnet masks, you rely on binary arithmetic. Binary arithmetic is the language of computers. It uses only 2 digits, 0 and 1. Despite its simplicity, it's incredibly powerful. In binary addition, we follow 4 basic rules. Let's walk through this step by step. First, read the binary numbers aloud. The first number is 1011, and the second number is 1101. We add starting from the rightmost bit. 1 plus 1 equals 10 in binary. That means we write down 0 and carry over 1. In the next column, we add 1 plus 0, which gives 1. Add the carry from before, and we get 1 plus 1, which again results in 0 with a new carry. Keep following this pattern for each bit. 0 plus 1 is equal to 10, write 0, carry 1. 1 plus 1 is equal to 11, write 1, carry 1. Finally, add carry 1 to a blank digit, write 1. The final binary result is 11000. Binary subtraction example. The first number is 1101, and the second number is 1010. We start from the rightmost bit. 1 minus 0 is 1. Then, 0 minus 1 requires a borrow, so we borrow from the next digit to the left. Let's go step by step. 0 to 1, borrow 1, becomes 10 minus 1 is equal to 1. Next, 0 after borrowing. 0 is equal to 0. Leftmost. 1 minus 1 is equal to 0. Putting it all together we get 0011. Segment 3. Octal arithmetic, base 8. Octal is used in Unix and Linux file permission systems. For example, the permission 755 means read-write-execute for the owner and read-execute for others. Octal numbers use digits from 0 to 7 and are based on powers of 8. Let's see how to perform arithmetic operations in octal. You can either perform direct base 8 addition or convert the numbers to decimal first. Let's convert. 172 in octal is 122 in decimal. 225 in octal is 149 in decimal. Add them to get 271. Then, convert 271 back into octal, which gives us 417. So, 172 plus 225 in base 8 is equals 417. Let's go step by step. Start from the rightmost digit. 5 minus 6 is not possible, so we borrow 8 from the tens column. That gives us 5 plus 8 is equal to 13. Then, 13 minus 6 is equal to 7. Now move to the tens column. Originally 4, but we borrowed from it, so it becomes 3. 3 to 4 is again not possible, so we borrow 8 from the hundreds column. Now 3 plus 8 is equal to 11, and 11 minus 4 is equal to 7. In the hundreds column, 3 becomes 2 after borrowing. Finally, 2 minus 1 is equal to 1. So the final answer is 177 in base 8. Segment 4. Hexadecimal arithmetic. Base 16. Hexadecimal is used in web development, memory addressing, and assembly programming. For example, colors like #FF5733 and memory locations like 0x7FFF are hexadecimal. Hexadecimal numbers use digits 0 to 9 and letters A, F to represent values from 0 to 15. They are compact and efficient, especially in digital systems. Add 6EB and 57E. Let's convert both numbers to decimal. 6EB is 1771 in decimal, and 57E is 1406. Their sum is 3177 in decimal. Now we convert 3177 back into hexadecimal, which gives us C69. So the final hex sum is C69. Subtract EB6 from D47. We'll explain the logic of subtraction by borrowing in hexadecimal. Let's convert the hex values first. D47 equals 3,399 and EB6 equals 3766 in decimal. Now subtract. 3,766 minus 3,399 equals 367 in decimal. Next, convert 367 back into hexadecimal. We divide 367 by 16. That gives 22 with a remainder of 15, which is F. Then divide 22 by 16. That gives 1 with a remainder of 6. Finally, 1 in hex is just 1. Write the remainders in reverse. 16F. So, 367, decimal, equals 16F, hexadecimal. Applications recap. Let's quickly review how these number systems are used in real-world computing. 10 decimal. Accounting, Excel formulas, financial apps. 2 binary. Logic gates, networking, e.g., subnet masks. 8 octal. Unix file permissions, e.g., chmod 755. 16 hexadecimal. CSS color codes, memory addresses, debugging tools. Each system has a unique role and is selected based on efficiency, simplicity, or compatibility with the task at hand. Conclusion. Great work today. You've now developed a solid understanding of how to perform addition and subtraction in 4 major number systems: decimal, binary, octal, and hexadecimal. These operations form the backbone of computing systems, from basic calculations to memory management, IP addressing, and even website styling. By mastering number system arithmetic, you're building the skills needed in programming, system administration, and digital electronics. In our next lecture, we will explore computer software, the digital instructions that bring hardware to life. We'll examine types of software, their roles, and how they interact with the systems you've just learned to calculate within.